In this video, we're going to be talking about internal energy and learning how to calculate internal energy for processes and also explaining why it's classified as a state function. Internal energy is the sum of all kinetic energy and all potential energies that an object has. So particles are objects, and so the internal energy is the sum of all kinetic and potential energies that particles in the system have. The internal energy is a state function. What a state function means is that the value depends only on the state of the system, and it doesn't matter how the system got there. So it doesn't matter on the path, it just depends on what it is. You can take many paths there, and they'll all lead you to the same spot. We can often talk about the change in energy. So we give this delta symbol here, it means change in, so that's a capital delta. And so that little triangle there means change in. So that's the Greek letter delta, capital delta, and that means change in. Whenever we talk about the change in something, we mean final minus initial states. So we talk about its energy it had in the final state, subtract the energy in its initial state, and then we get the delta energy. So that we always do final minus initial. So here's an analogy for that whole state function thing. Think of a state function as altitude. There are many different paths to the top of this mountain. We can either go the zigzaggy path and make it to the top, or we could take the shorter path and make it to the top. This path here, it is longer, but still leads to the same spot. So the paths are different lengths, but they all reach the same altitude. Therefore, altitude would be a state function, and the distance to get there are not state functions. So distance traveled is not a state function, but the altitude would be a state function. So internal energy is a state function. And we can talk about the change in energy by looking at the energy of the initial state, which would be like our reactants, and then the energy of the final state, which would be our products. And so when we find energy for a reaction, we always do final minus initial. So final is the product's energy, and initial is the reactant's energy. So this energy diagram here is kind of like showing the altitude of things. So it's showing you the initial and final energy. And so it's kind of like what altitude did you climb during a reaction or not. So we can have energy exchange between the system and surroundings in either direction. So for instance here, the reactants are higher in energy than the products. And so when we do final minus initial, we end up with a negative value. And that means that this reaction is exothermic. Our reaction is losing energy to the surroundings. So our surroundings are gaining energy, and our system is losing energy. So you always have to think about yourself from the perspective of the system, what you're studying. And so here you're losing energy to the surroundings. And so your system will have negative energy and your surroundings will have positive energy. The surroundings are gaining the energy, the system is losing the energy. So the negative sign here indicates that it's losing the energy. In the opposite direction, if your delta E for your system is positive, that means that your system is overall gaining energy. So your energy is flowing from your surroundings to your system. That means that you're ending in a higher energy state than you started. So products minus reactants will be a positive value. So this sign here does tell you the direction of the energy flow. Is energy flowing in or is energy flowing out? When you do have energy flowing into the system, then this reaction is called endothermic. And the sign tells you. You always have this relationship between the surroundings and the system, because remember, any heat lost by the surroundings is gained by the system. So if delta E system is positive, then your surroundings would be negative, and they would be equal and opposite numerical values. So if one's negative 500 kilojoules, the other one is positive 500 kilojoules. So summarizing what we just talked about. If the reactants have higher internal energy than the products, then your delta E system is negative and energy is flowing out of the system into the surroundings. If the reactants have lower internal energy than the products, then your delta E system is positive and energy is flowing into the system. So energy is like money again. If money is leaving your account, you might end up with a negative account balance. If money is entering your account, then you have a positive increase in your account balance. Let's do a conceptual practice problem. Consider the fictitious energy gauge here, and that describes its initial and final conditions. In which case, well, in which case does it correspond to, like, if these are the final conditions, this is the initial, which final condition indicates a delta E system that would be negative? Read the slide. I didn't articulate that well, but it's there. Okay. Hopefully you got some thoughts about that conceptual problem here. And let's think about this. So it says delta E system is negative. So your system needs to be negative. That means it's going to be going lower. So which of these is going lower than where it started? So it started right here on the top notch. And so this one is lower. This one is lower. And this one is higher. So it can't be that one, because that one, the delta E system is positive. And we're looking for delta E system that's negative. Next up, let's look at the difference between these two. This one went down one notch, and then the surroundings went up one notch. This one, the system went down one notch, and then the surroundings didn't increase at all. So this one is violating conservation of energy, because the surroundings didn't gain anything. And so we always have to have this equal and opposite relationship. So if the system went down one notch, the surroundings have to increase one notch. And so A shows that principle here.